Greetings, everybody. Thank you very much for being here. My name is Lazaros Moysis. I'm from the physics department of Aristotle University of Thessaloniki, back in Greece. And today we're going to discuss about a novel chaotic system with application to secure communications. I'm funded personally by the Greek State Scholarship Foundation, and Professor Pham is funded by his own Thessaloniki University. So let's begin. We're going to discuss about 4 topics today. First of all, we're going to discuss chaotic systems and explain what is chaos. Secondly, we're going to propose our own novel chaotic system, see how this system can be applied to the problem of chaotic secure communications, and then we're going to discuss future research directions from this work. So let's begin. What is chaos? I'm sure you have all heard the term. And, in physics and mathematics, by chaos, we refer to deterministic systems that showcase an extreme sensitivity to initial conditions and parameter changes. And by that, we mean that the system by no means are stochastic. So we talk about deterministic systems that showcase an extreme sensitivity to initial conditions. And by that, I mean that if we change slightly the initial value or a parameter of the system, the solution trajectory will be completely different from before. And I can easily showcase chaotic behavior with a couple of simulations here. So let's see the first simulation. Here you will see that I have 3 pendulums, wait until it resets, and they start from almost identical initial conditions, almost identical. And you see that after the second or third second, the trajectories of the 3 pendulums become completely different. So this is an indication of extreme sensitivity to initial conditions and hence chaotic behavior. In our second simulation, I have 2 balls bouncing on a sphere, and they start again from almost identical initial condition, initial point, but after the third or fourth bound, you will see that the trajectories diverge. Let it reset for a moment. You will see it right here. So you will see that after just a moment, fair, 1, 2, 3, after the fourth bounce, the trajectories become completely different. So these 2 simple mechanical systems are clear examples of extreme sensitivity to initial conditions and hence chaotic behavior. And chaotic systems indeed are all around us. They can be found in biology, in engineering, in physics, in electronics, in chemistry, in astronomy, everywhere, all around us. And they are also extensively used in encryption-based applications because they are deterministic. They give, as you can see here, a completely random behavior and unpredictable behavior. So they are very handy, if you like, to be used in encryption-based applications. And that's what we did here. So, we always want to propose novel chaotic systems to be used in such an application. And this is what we do here. We have a simply 3-dimensional chaotic system, that you see right here. You will see that it has no linear terms. It also has only 2 parameters, A and B. And later we will see that the system has a chaotic behavior for a very wide range of parameter values, which is also a very nice property. It is also dissipative. You will see that it has actually a lot of cubic and absolute terms, and these are very commonly used to induce chaotic behavior in a system. And also, more importantly, this specific system has an infinite number of equilibrium points, and they are all located on a line of this form, 0, 0, Z. So this system with a line equilibria is a special system that belongs to the category of systems with hidden attractors. So such systems are a very trending topic of research among physicists and engineers because many works have shown that they are very, very, very handy in encryption-based applications. They have a lot of nice numerical properties that make them, not going into detail, much more handy in encryption-based applications. So, when designing a novel system, we always want to have this additional property, ideally. So this is our new system. Let's see, for example, its chaotic attractors. The shape is like that. Here we see simulation for alpha equals 0.5 and beta equals 0.1. Now, in order to extensively study the chaotic system, I have basically 2 tools, the bifurcation diagram and the Lyapunov exponent. So let me explain them very fastly. Oh, also here you see the sensitivity to initial conditions. Here I have a simulation for almost identical initial values, and you will see that after the 300 seconds, the solutions of the system completely diverge. So this is an example of a chaotic behavior, of course. Now, for the bifurcation diagram, what does it plot actually? For the bifurcation diagram, what we do is let's see here, for example, a simulation for alpha equals 0.5 and the attractor of the system. What I do is I plot the points of intersection between the attractor and the plane x equals 0. And let's say I also choose a direction of movement for the system. And here I see, for example, in what points the attractor cuts this plane, which gives me an indication of the system having chaotic behavior or periodic behavior. Now, if I plot these points, for example, for alpha equals 0.5 right here, okay, and I also do this for an extensive number of values for parameter alpha. For example, here I plot it for from 0 to 0.7. I get this diagram of this sort. And this diagram, what actually does is show me where does the system cut the plane x equals 0 in more than one point. As we see here for alpha equals 0.5, and for most of the points right here, for most parameter values, I see that the system cuts the plane in many points, which actually is an indication of chaotic behavior. And for example, I see that there are only just a very few points, like right here, 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 and here, where the system cuts the plane in only 1 or 2 points, which is an indication of periodic behavior. So what this does is actually tell me that for most parameter values, the system here is indeed chaotic. And we want that. We want to have a system that for most parameter values behaves chaotically. So we have a very robust behavior, if you like. So this is a very good design. As you see, we're very satisfied with the behavior of our system. And we can verify that using the second tool, which is the Lyapunov exponent. Roughly speaking, what does the Lyapunov exponent show? It indicates whether two chaotic trajectories, starting from almost identical points, quickly diverge or not from each other. So if the Lyapunov exponent is positive, the system is chaotic. Indeed, we can verify that for most parameter values, you will see that the Lyapunov exponent has a positive value. Of course, there are some very, very small points where the system becomes, again, periodic. So the chaotic behavior is lost, but only on very, very, very few points. And I can actually verify that if I overlap the two diagrams. You will see that the Lyapunov exponent is indeed positive on all those parts where I have a lot of cuts with the plane x equals 0, and the behavior being chaotic in only very, very, very few parts. So this is the desired behavior here. We want to have a system that is chaotic for most parameter values, so we can use it then in an encryption scheme. And that's what we present here. We will present the symmetric chaos shifting modulation method for chaotic secure communications. Now, what we want to do in a chaotic secure communication design. What we actually want to do is, let's say we have an information signal, which is usually binary, because you can represent a lot of information with binary signals. What I want to do is take this information signal and use it and combine it with some way with the trajectory of a chaotic system, and scramble the information signal, mask it if you like, and then I can transmit the scrambled information securely from a transmitter to the receiver. And then at the receiver end, I would like to reconstruct the scrambled system so that I can receive back the original information signal. And this is what we do here. So in the transmission step, what I do is this. I take the supposed information signal, which here has a transmission period of 1 second, and I also take the state x of the original chaotic system that I propose. So I take these two signals and I multiply them. And with this way, I can manage to scramble, if you like, and mask the original information signal. Then I can transmit this scrambled signal. And of course, here we assume that the transmission is noisy. So we say that we potentially have some additive Gaussian white noise added to the system. And at the receiver end, what I do to reconstruct the system. First of all, I take the scrambled information and I multiply it again with the same signal from the same chaotic system. So this is why we call this design symmetric, because in the transmission and the receiver part as well, we use the same chaotic system. So we multiply the signal again, we integrate it in a discrete integrator. So we integrate it every 1 second, which is the period of the information signal. And this way we can compute the bit energy of the transmitted signal. And this way, whether the bit energy is positive or negative, we can estimate the original information signal again and appropriately reconstruct the information signal. So let's see zoomed out all these signals again. So this is the original chaotic signal that I use, the first state of the system. this is the supposed information signal that I want to encrypt and potentially safely transmit. By multiplying them together, I get this modulated signal. Of course, once it is transmitted, it becomes noisy, and then at the receiver end, we can reconstruct, as you see, the original information signal again. So this is our design. Of course, by doing a bit error rate performance with respect to signal to noise ratio, we can actually see how the bit error rate performance and the system performs, which is very satisfying. So overall, we have a very nice design. We see that the communication scheme works pretty well under any type of under any amount of noise here. So we have an overall very nice design. Now, of course, this design, I'm very satisfied to say that we can extend it and modify it and have a lot of different modifications of this technique, even more advanced and potentially even more secure. So as future topics of interest, I'm interested to say that we can do an extensive BER, bit error rate analysis, with respect to different parameter settings and compare it to different chaos-based techniques and potentially have an even more, advanced design. Because here we can do a lot of modifications for this design, which is very simple, but we can actually add simple modifications and improve it and make the chaotic system, the masking signal, even more secure. So we can potentially have an even more extensive and complete design. And secondly, what I'm really interested in doing is, potentially have an experimental implementation of this design. So first of all, here we did the simulation in MATLAB, but we can potentially extend it using microcontrollers and first, using some form of Arduino boards to simulate the design. But also what I really want to do is to have some form of wireless implementation of this design. Here at the physics lab in the physics department, we have a very well-equipped lab, and I'm pretty sure that in the near future we can manage to apply and implement this using wireless parts. And I'm really interested and excited to see this being done in real practice. And of course, for the proposed system, we can have a lot of other encryption-related applications, because we see that the system is very well in its chaotic characteristics. So potentially, we can also apply the system to the problem of pseudo-random bit generators or potentially to image encryption. So I'm very excited to say that overall, this is a very nice work. This design is very nice, and we can potentially extend it to many different directions and have an even more secure design that has even better simulation results with respect to bit error rate performance. So a lot of new works to be done, from this specific paper. Now, as a closing remark, please let me add that me, along with Professor Volos, have an upcoming special issue on electronics called Recent Advances in Chaotic Systems and Their Security Applications. And I'm really interested to see, new submissions here. By all means, if you are interested, feel free to contact us. So that's all I wanted to present today. Thank you very much for being here. Unfortunately, due to health reasons, I couldn't be there myself. I'm very sorry for that. I really hope you all stay safe during this very weird time. And I also need to mention that we are always interested in new research ideas and new collaborations. So by all means, if you are interested in our work, feel free to contact me. We can discuss it further. We can discuss future extensions of this work and also collaborations with each other. So please keep safe. Feel free to contact me about anything. And thank you very much for your time. Kind regards. Bye.